So now I want you to imagine that you're blowing up a balloon, okay? And we're going to do a graph of pressure in the balloon against time, okay? Now, when you start blowing up a balloon, alright, there's no air inside the balloon, so it's relatively easy to blow up. So pressure within the balloon to begin with will increase fairly quickly, okay? But as you put more and more air into the balloon, okay, the pressure pushing back on you from inside the balloon increases, and it gets harder to inflate the balloon. So after a certain while, pressure will start to increase more slowly, okay, and slower still as time goes by, and as you put more in, and slower still, until it reaches the point where the pressure inside the balloon, okay, is equal to the pressure inside your lungs. So you can no longer inflate the balloon any higher. This is essentially what happens inside a capacitor. As you put more and more electrons onto one plate of the capacitor and more positive charge onto the other, the Coulomb force pushing back becomes greater, and it gets harder and harder to put the electrons in. So the rate at which the voltage across the capacitor increases, okay, starts off very high and then drops off, okay, until it reaches a maximum where the voltage across the capacitor is equal to the voltage of the supply, okay. So the maximum voltage here is going to be Vs, the voltage across the supply. We can also think about that in terms of current in the circuit, okay? Now, initially, when there's no electrons on the plate, there's no Coulomb force, so it's very easy to put the electrons in. They'll flow in very quickly. So we'll start off with a high current, okay? But then as we get the bigger Coulomb force, it gets harder to put the electrons in. The rate at which the electrons will flow onto the plates will drop, and the current will drop off, go down, 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 until the current in the circuit is zero, okay? And that makes sense. When the voltage across here, VC, is equal to the voltage at the source, Vs, there's no voltage drop left to be across the resistor. By V equals IR, if the voltage across the resistor is zero, then the current through the resistor must also be zero. So if there's no voltage drop here, there's going to be no current. So at the point where the voltage across the capacitor, when VC, the voltage across the capacitor, equals Vs, then I equals zero. Okay? It will charge up the capacitor, we call it charging the capacitor, to the point where it's at the source voltage and the current in the circuit is zero. Let's look at this better graph now of the charging of a capacitor. Again, see the maximum is at Vs, the voltage of the source, but there's an important factor that you need to include when you're sketching these graphs, okay? And that is called the time constant. Now the time constant is defined as tau, which is a Greek symbol, little curvy t, and that equals time for capacitor to charge to 66% of final value. Okay, that's what the time constant means. And if we were to calculate 66% of the source voltage, that would be 0.66 Vs. We find that's about here somewhere. And so tau, time constant, is how much time it takes to charge to that value. Okay? Tau. Now, for a circuit like this one we saw just here, okay, where we have a resistor and a capacitor, we have the formula tau, time constant, equals RC. Okay, where R is the value of the resistor. Okay, the resistor here in the circuit, and C is the value of the capacitor. C is the value of the capacitor. Values of capacitors are given in units known as farads, and the symbol is F. So if you want to find out how long it takes for a particular circuit with a capacitor and a resistor to charge to 66% of the final value, you can use tau equals RC. And we usually say that for a circuit like this, the time it takes to charge to its full value is 5 tau. Okay, it'll take 5 time constants, okay, for the capacitor to reach its final value. So that showed us how the time constant relates to a charging voltage, okay, when a capacitor is charging. But we can also draw graphs that show similar things for when a capacitor is discharging, and the voltage goes from being very high to very low. Time constant is how long it takes for it to discharge 66% and get down to 33% of its original value. And we can also do similar graphs for the current. In each case, the time constant for both charging and discharging, okay, the time constant tells you how long the current takes to drop to 33% of its final value. That's hopefully introduced capacitors to you in an adequate fashion. Capacitors are a way of storing charge. They're created by a very thin break in a circuit between two plates. They stop charging when there's a balance between the applied electromotive force and the potential difference that develops between the plates, and we can draw these charging and discharging curves for them, in which the time constant, tau, is a very important factor. It works for voltage, charging and discharging, and it also works for charging and discharging current. Remember, the time constant, tau, equals RC, resistance multiplied by capacitance.